Welcome to a read along with Dr. Pell in the book Discrete Perspectives in Mathematics. This is subsection 4.4.4. We've just discussed how an elliptic curve like this one actually can have if you have a vertical line, there really is a third intersection point. It's just one you can't see. And we're going to call it the point at infinity. So if you read through the end of this section, we're going to call it the point at infinity here. Okay, so this subsection talks about choosing an identity element in here to kind of make things work, or something that not just an identity element, but an anchor. There are some problems if we just say if the sum of 2 points is the third point. That doesn't quite work as well as we'd like to. We do know that finding the third point from two beginning points is indeed well defined. We just kind of were looking at that. But having a point that acts like an identity with respect to this addition is actually impossible if we said that. So here in this paragraph, we have an idea. So let I be the proposed identity point, A another point, and let's suppose that the third point on the line between I and A would have to be A, right? Because if you were using this idea that I plus A is the third point, A. But this means that the line must be tangent to the curve at A, because there's a double multiplicity, right? Because the third intersection point would be A, so A would be like double counted. So it would have to be tangent to A, okay? Okay, but you know, this is a little bit of an issue because the point A is arbitrary. So it's randomly picked, which means that any line that goes through I and another point on the curve must be tangent to the curve. And not at I, but at the other point. Okay, just try drawing such a thing for a minute. All right, see if you can do it. All right, okay. So let's see if we can draw such a thing. So we need a point. So we have okay, so let's suppose we have an identity element, I, and this is on the curve, all right? And take another point, A, and when we draw a line through this means the curve has to be tangent to A. But, okay, then if we put a point B and we draw a line through it, that means the curve has to be tangent at B, right? But wait a minute, what about a point in between right there? And it doesn't look tangent there, does it? Actually, try as we might, probably the best thing we could do is I and have a straight line, right? Just a straight line. And then this line is always tangent to the curve. If the curve itself is a straight line, maybe that would work. Or maybe, okay, so a line through there. Yeah, okay. So in essence, this doesn't look that good for the types of curves we want to consider. We're gonna fail at getting an identity element, especially the curve that we've been looking at right here. We wouldn't be able to get an identity based upon this idea of using the identity and thinking about double multiplicity having to occur on that line. So there's a workaround. The workaround is getting an anchor. So using this third intersection idea, but then using an anchor to help us out a little bit. Okay, so let's go to that point. All right. So how are we going to get around this? We choose an anchor point. So suppose we have an anchor right here. Let's just choose an anchor here. And this is how we're going to get A plus B. All right, if we have an A and a B. We have a third intersection point, C, but let's not choose that. Instead, let's have an anchor point, and we're going to take the line that goes between that guy and the anchor, and then take its third intersection and call that A plus B. And that actually works. We are able to have an identity element. In fact, the identity element will be the anchor itself. So, for instance, if we want to add A and the anchor together, right? We get the third point, right? So the third point on that line, and then we look at the line from O and the third point, which actually happens to be the same line that goes through A and that third point, and we get A. Let's illustrate that by drawing that out. Okay, so let's take a look at that. So let's see here. If I were to draw a line that goes from A, let's just make this look straight. Let's see here. A. Well, you get the, let's see, that's not quite right. Maybe we should, all right, let's just try this again here. Let's maybe just get a straight line. Okay, let's go from here. Get a straight line to the anchor. All right, okay, actually there is a third point right in here. So there's a third point, and the third point will be right around here. Let's call it B. All right. So we want to add A plus O. So we go to the third point. Then we draw a line from between that guy and the anchor, which is the same line we're on. The third point of that line is, again, A, meaning that A plus the anchor, which we'll call O, is equal to A again, just as desired. So this anchor actually resolves the identity issue completely. And actually using it, we have all other features that we'll need for our group. We just have to figure out a good anchor, but really about any anchor would do, and we'd have a group in this case. All right. So, and this kind of describes what we were just discussing. Okay. And all right, what about inverse? Remember that B that we actually found? Let's see. So we have A, B, and anchor. Maybe we should draw that again and just look at that, because that's what this is discussing down here. It's discussing that. Okay, it's discussing inverses. So let's take a look at that. What if we were to come here, draw a line, all right, and then let's look at the point B. Actually, there's a B right there, so maybe we shouldn't use B. Maybe we use like D or something. All right, D. All right, so we know that, let's try to compute what A plus D is. So we draw a line through A and D, and we look at the third point. The third point is O itself. Okay, third point is O itself. Now let's try to draw. So then what we're going to do is we're going to draw a line through O and O, since O is anchor. So really we're going to go with O plus O. All right. Now O plus O, if we were to add O plus O, what we would do, let's think about this. We take a line that's tangent to O. Take a line that's tangent to O. So maybe we'll get out the line tool here. Draw a line that's tangent to O, because how do you add O plus O? You need to find the line that has an O and an O on it, which is precisely a line that has multiplicity, that intersects O with multiplicity 2, so it occurs twice on the line. All right. So we take this. Okay. So yeah. Okay. So so just imagine that this intersects here. O right there. O plus O. Okay. So that's going to hit, and that line actually is going to, it's probably going to just draw this again here. So imagine this is tangent, and it's going to hit the curve up here somewhere. So it hits it up here. So that's the third point of O plus O. Then what we do is we take the line between O and that third point, and we end up getting O back because O happens twice because we're adding it to itself. So it looks like that we end up getting O out of this sum here. A plus D is actually equal to O. Kind of reviewing that process, what did we do? We went A and D, found the third intersection, right? Then we find the line between O and O, which is a line tangent to the curve right at O. So if I take the line tangent to the curve at O, because it has an O and an O on it, and you look at the third intersection, which is up here, then you take that third intersection and you match it with the anchor. But this line already had O as a double multiplicity, so the third point would be O again, meaning that A plus D is actually equal to O. So actually, this anchor idea actually gives inverses as well. So not only do we have an identity, but now we even have inverses. And because we always have third intersection points, it's closed. It's well defined. So it looks pretty good. The only thing we're really missing is associativity, which is a little bit harder to show with these groups, but it actually does hold as well, if with a choice of an anchor. So we'll need to talk about associativity as well, but one key aspect, remember that every single line has a third intersection as long as we consider multiplicity or tangency. If a line is tangent at a point, that point's double counted on the line. So let's just this is just a key point, so I think it's worth remembering and discussing. So we have a point from here, okay, a line from here, and we go this way. Imagine that it intersects right there, at a tangent, and intersects there. So that means if you want to add this point plus this point, the third point would be on the line, would actually be right here because this point's counted twice. So if you want to find a third intersection with this and a point right here, it's the other point. Okay, so that's one thing in the argument that we were using. And so I just wanted to make sure that was clear as we go along here. All right. Okay. So, so the anchor point's really good. Now, what's a good choice for anchor? Actually, a nice visual choice for the anchor is not to just choose any point randomly on the curve, but actually use the point that you don't even see, the third intersection point, or the point at infinity, the y-axis in that picture. Remember in this picture, that green line that's off the curve? We're going to use that as a point, and that's going to be our anchor. Why is that such a good anchor to use? Well, for one, vertical lines always intersect it. So if you want to find inverses, it's as easy as finding vertical partners. Points that are vertical from each other will be inverses to each other because they are on the same line, if you will, as the imaginary infinity point off the line. You can imagine, if you want, you can just imagine thinking of vertical lines that pass through this picture, and the magical point in infinity is the one that's on every single vertical line, kind of down at infinity somewhere. That's another way of viewing it if you want to think two-dimensionally, just in the plane. So that's actually a great anchor point because it's easy to see inverses, and that's the one that's standardly used. However, any anchor would actually do. So using that idea, that's kind of nice, and since I is the anchor, I also will serve as the identity as well. Okay. But the idea is if we change the anchor, though, our whole addition structure changes, and what the identity changes, and what inverses change as well. So you have to just remember that as we move along. All right. So here's just a picture here of this. So I want to use negative p as the additive inverse of p. So p and negative p, they're inverses of each other because they occur vertically from one another. And this is the magical point in infinity, which you don't see. Um, and we're going to say it's own vertical partner, because actually if you were to look at that curve, um, actually we get that, or the surface, the blue surface. If you thought about multiplicities with this blue surface, it actually intersects with multiplicity 3. So this y-axis point is really um, right here, the y-axis itself. Um, let's see, let's just take a look at that. What it says here, the tangent line at infinity intersects with multiplicity 3. So what's the tangent line at infinity? The tangent line at infinity is actually the line, the plane that is tangent to the surface at the y-axis. Now, the plane that's tangent to the surface of the y-axis, if we were to look at that a little bit more, it's actually flat. It actually is parallel to z equals 1. It's actually the plane z equals 0. That's the tangent plane. And that tangent plane doesn't intersect any other lines. But we do know that if any of these intersect two things at 2 points, and for tangency it's double counted, then it intersects at a third, which actually means that that plane um, intersects three places. I didn't really go through a proof of that. That's a little bit more algebraic. However, we're going to take that for granted that we can that idea of multiplicities. Okay, so the point at the tangent line actually has multiplicity 3 as we go along, but nonetheless, even with the anchor idea, however we look at it, like we showed above, once we pick an anchor, we know that it's going to, if we add it to itself, it's going to be 0. So it's its own inverse. So we can think of it as its own vertical partner as well. So every point here has a vertical partner. Okay. So, all right. So here's the adding process. First, find the third intersection point, and then, oh, this is interesting. Remember up there we're thinking of using an anchor and having to intersect the point with the anchor, and then looking at the third point. Basically it just means turning to vertical lines, because the vertical lines are the ones that go through the point at infinity now. So that's a nice choice of anchor, because the first line is just a line that we need to get a third intersection point. The second line is a line with the anchor, but all lines with the anchor in this case are just the vertical lines. So the second line will always be easy to draw. It's just a vertical line, which is really nice. Nice reason for choosing this as your anchor. So here, like for instance, if we want to add a plus b together, let's see what's really going to happen. We take a and b, we go to the third point, the third intersection point, and then we draw a vertical line down here, because that's going to intersect the point at infinity. And the third intersection point with C and the anchor, which is the point at infinity, will be A plus B. So basically, it's just you find the third intersection and go to its vertical partner. Third intersection, vertical partner. Third intersection, vertical partner. It's simple as that. So so we can even forget this line and just think, okay, what's A plus B? We draw a line through A and B, we find the third intersection point, and then just go vertical partner. We got it. That's how we add the points on an elliptic curve together. And it's a well-defined addition process. It has inverses, it has identity, but see this coming up, associativity. So we'll save that for the next little video. Thanks for watching.